Hello world and welcome to the fourth video in this series on creating an IK-driven procedural walk animation. In today's video we are going to teach our spider not to drag its feet. So we are going to get our foot to stop doing this and start doing this. Let's get to it. My name is Mani and I make games. Now, before we start getting into the explanation, a few things. Firstly, I've included useful links for this video down in the description. Go check it out. As always, the link to the GitHub page for this project is down there as well. If you like this video, hit that like button and maybe even subscribe and ring the bell. Okay, let's look at our symbology here. Now, as you can remember, the yellow is the effector. That's effectively our foot or the end of our IK chain. The green here is our target, which the effector will always try to reach. And this gray blob down here, that's our foot placement target. That's the ideal position for our foot. So in other words, that's where we want our foot to end up on every step. Now this moves with our body. Like this, and then this needs to try to catch up. This mysterious red blob up here, I'll explain a little later as we get into the walk cycle. It's a little debugging tool that I've set up for us. Right, let's look at what we need to do. In our walk cycle, we want to get our IK target from one point to the next point. So as soon as this distance becomes greater than step size, then we want the foot to move from here to here. Now currently we are teleporting. In other words, the foot just goes bam, bam. I'm pretty sure that defies the laws of nature, so let's see if we can make it a little better. We also don't want our foot to do a shuffle by dragging itself over here. We want to get a nice step going up to a high point and down to the end point. Okay, let's see how we're going to accomplish this. We need to do a little bit of vector maths. Check out the description below for some useful links on that. Now let's see. Let's suppose that our IK target is currently at a point with coordinates 5, 5. That means the x is 5 units on the x-axis away from 0, and the y is 5 units up away from the 0 point on the y-axis. Then the final point where we want to place our foot is going to be on 7, 5. So we need to get this point. To figure out what this point is, we need to find a point that's halfway between the 2 points and up by a certain distance. Now if you look at this, it's actually pretty easy to get it in your head. You grab this and this, the difference is 2, so add 1, you get 6, 5, and then you can add the step height up here, which gives you 6 and 6.2. But things are going to be different if you have an inclined plane that you're walking on. So to make sure that we don't have to go back and change things later, let's start off with vector maths from the very beginning. Okay, so let's do the vector math for this. First, we need to find out the vector for reaching this point from here. To do that, we take our destination, 7, 5, and we subtract our start point, and there we go. So to get from here to here, we need to follow a vector with an x component of 2. That means we're moving 2 in the positive x direction and 0 in the y direction, straight and level. To get the middle of this, we would just simply go take that vector and divide it by 2, which gives us a vector of 1, 0. In other words, to get to the middle, we move 1 unit to the right, and we're there. We have our middle point here, but we also need to go up. Now we can take this vector to get a vector for your step height. You can take the vector for up. In this case, it'll be simple because we have a 0 x component. And we do 1 here to get a vector that points straight up. Then we times it by our step height, which is 1.2, which actually gives you a vector of 0, 1.2, like this. That means we have a vector pointing straight up with a magnitude of 1.2. So where does this leave us? We now know that we can take this point, 5.5, 5, and we add 0, my mistake, and we add 1, 0. That gives us a point in space of 6, 5, which is here. And the vector to get from here to here is this one here, our vector pointing straight up with a magnitude of 1.2. So we take 6, 5, and we add 0, 1.2, and we get a point with the coordinates of 6 and 6.2. Now that we have our coordinates for our start, our high point, and our end point, we're going to go into code and figure out how to get from here to here and from there to there. And to do that, to figure out how fast we're going to do that, we're going to use something called our foot speed. So let's jump into our code and see what's going on. Okay, here's our code. Let's look at what I've added since last time. I've added an enum and I've called it step phase. This is going to track which phase of our step cycle we're in. We have planted. This is going to be the phase where our foot is on the ground. It's basically where the foot placement target is, and it's standing still. Then we have lifting. We've realized that we're too far from our foot placement target and we're starting to move towards our high point of our step. And then moving to plant means we've passed the high point of the step and we're moving down, back down to our new position. To track the current step phase, I've created a step phase variable and set it to moving to plant. The reason for this is that if our spider's set up and we have our foot placement position set up, then when we start the scene, the spider will automatically start to move its feet towards the desired positions. Okay. Then we have our foot speed variable. This is going to determine how fast we move our feet. Instead of teleporting, our feet will actually move from one point to the other. And here we have next target. Next target is going to track where our foot's supposed to be heading in the moment. So let's say we are at planted and we shift to lifting. Next target will be set to the high point and the foot will keep moving towards this target until it reaches the high point target. Then our state will change to moving to plant and the next target will be set to our final destination. Then I've just set step height, which determines how high we lift our foot, and our distance tolerance. The reason why I use this is because if you are moving towards a vector, you might get very close, say to within 0.0005 units of it. But that's not zero. So if you are going to do an if statement to test that you've reached the destination, you might end up getting a false when you are actually so close that you might as well have reached the destination. In this case, it's good to have a distance tolerance variable where you can say, if I am closer than this to the point I want to reach, I'll say that's good enough. I've reached the point and I'm moving on. Let's look at that implementation. Okay, update. We're still doing the check to see if our foot placement target is further from our current position than the step size. If it is, we should do something. But now we've added only if our step phase is planted. That means if my foot is not planted, I'm not going to try to change the step phase. And I'm not going to initiate a new step. If both of these conditions return true, then we change our step phase to lifting because we're about to start moving our foot. And we set our next target using the find lift position function. This is a function I've written that actually returns their lift position by calculating it as I've shown you in the explanation. We'll look at this function in a moment. We have our lift position, we are moving to it, and every frame moved foot will move to our next position, our next target. Then finally, we get closer to that target than the distance tolerance. And now we get to do something again, but only if the step phase is lifting. If the step phase is lifting and we are closer, we check, we set our step phase to moving to plant because we passed our high point, and we set our next target to the foot placement position. Now we're currently moving down to our foot placement position in every update frame. Then finally we get close enough to our foot placement position we check that we are in the moving to plant step phase. If that is true, it means that we have now reached our final destination, and we plant our foot and we wait until the next step needs to be started. Okay, move foot gets called at the end of our update. All that does is to move the foot. We'll explain this a little bit later, but first let's look at find lift position. So find lift position starts off by finding the difference vector. In other words, this is the vector to go from our current position to the find placement position. That's that vector that runs along the horizontal plane from your first starting point to the end point. Then we take that, we divide it by 2 to get the middle, and we add vector2.up. That's a unity shorthand for a vector with a x0 and a y1. So that's a vector pointing straight up times the step height. In other words, how high we should lift our foot. And then we return that and we add it to our current position to get our final lift target. Right, just a quick note here. Currently we're using vector up, and this is fine when you're on the straight level plane. But later on, if we are walking up an inclined plane, we might have to use the transform.up for our spider. I'll explain this when we get there, just keep it in mind. Okay, move foot. I've changed it a little bit. We're setting our transform position as usual, but we're using vector2.move towards our foot target's current position towards the next target, and we're moving that at a speed of foot speed times time.delta time. Now time.delta time is how long your game takes to do one update or one frame. So if your system is running fast and you're doing 120 frames per second, that means time.delta time is going to be 1/120th of a second. If we times that with foot speed, it means that in this frame, your foot will move 1/120th of the foot speed. So we'll be moving along this vector at 1/120th or 1/30th or 1/60th of a frame. It all depends on exactly how fast the system is you're running. This means that we'll get a consistent foot speed across different systems with different performances. And then the last thing, this is our mysterious red dot. It's a little something I put in for debugging to help us spot any problems with our walk cycle. On draw gizmo is a unity message. So if you actually start typing on draw, you can select it there. This function is on draw gizmo selected. It's the same, except it only draws the gizmos for your object if it is selected in the editor. We want it to draw all the time, so we're using this. We say gizmos color, we set it to red, and then we say every time on draw gizmos gets called, draw a red sphere and place it where next target's position is. And this is the radius of our sphere, which is 0.4 units big. All right, let's save. and go look at how this works. Here's our spider. Let's play. And there we go. Immediately you can see the foot has moved to the foot placement position. Now let's move off to the left. It's going very fast. Let's slow this down. Make our foot speed 2. And let's walk. Now you can clearly see the walk cycle in action. Now obviously when the foot speed's this low, the walk cycle doesn't keep up with the speed of our character. So that's something that you can tune when you finally build the character and the animation that you want. Now there's another problem here. Let's just fix our foot speed first. Let's see if you can spot it. Our foot placement target goes exactly where it needs to be in relation to the spider body. But because our IK target just goes for the foot placement target, it steps on air. Now this isn't very natural. We want to put our foot there on the actual terrain. In the next video, this is what we'll be doing, and we'll be using something called ray casting to do it. Until then, I am Moni, and I make games.